Welcome viewers, in this video we'll see the details about the Millman's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Millman's theorem, one of the theorem available in the circuit theory. So this theorem enables a number of voltage or current sources to be replaced by single voltage source or single current source. So the main objective of the Millman's theorem is with n number of voltage or current sources can be replaced by a single voltage source or single current source. Now we'll see the statement first for the voltage source by referring the voltage source. Then we'll go to the current source. In any network, if the voltages V1, V2 up to Vn with internal impedance Z1, Z2 up to Zn respectively are in parallel, then these sources may be replaced by a single voltage source with V in series with the impedance Z. Refer this diagram. So we have voltage sources V1, V2, Vn, right? N number of voltage sources available. In each source we have the impedance Z1, Z2 up to Zn, right? So the voltage sources are connected in parallel that can be replaced by a single voltage source with a single impedance. V is a single voltage source V with a single impedance Z. This is a terminal AB. Terminal AB we have n number of voltage source connected in series with the impedance that is replaced by single voltage source and impedance. Now we see how to calculate this, the value of V and Z, voltage and impedance. So the voltage V is nothing but V1 into Y1, right? So this Z1 is available, impedance. Y1 is nothing but admittance. 1 divided by Z1 is nothing but the admittance. So V1 into Y1 plus V2 Y2 plus up to Vn Yn divided by the sum of admittance Y1 plus Y2 up to Yn. So by using this formula we can calculate the voltage, resultant voltage V. Similarly the impedance Z equal to 1 divided by Y1 Y2 up to Yn, right? So the n number of voltage sources connected in parallel replaced by single voltage source with impedance. The single voltage source V is calculated from this formula. Impedance is calculated from this formula. Y is nothing but admittance. So in general we can write it as V equal to sum of V into Y divided by sum of Y. Voltage into admittance divided by sum of admittance. The Z is nothing but 1 divided by sum of admittance. So in the given circuit converting each voltage source into equivalent current source. Now we'll see the proof for that, how we are getting this formula. So this first we'll consider the voltage source, that is now we are going to convert into current source. Now we'll see the diagram, how we are converting from voltage source to current source. Now refer this diagram, we have the current source available in parallel with impedance is connected. This is the first current source, second current source and third current source. Now that is converted into current source in series with parallel with the admittance Y1, I1, Y1. Similarly I2, Y2, I3, Y3, right? So the current source now converted into the current source with the admittance. Now we'll see the formula for that. I1 equal to V1 by Z1. So this 1 divided by Z1 is nothing but Y1. Admittance and impedance both are reciprocal, right? Impedance means opposing the current, property opposing the current. Admittance means allowing the current. So that 1 divided by Z1 is Y1. Similarly I2 equal to V2 by Z2, that is V2 into Y2, admittance. Similarly I3 equal to V3 by Z3, that is equal to V3 into Y3. Right? So this Y1 is nothing but 1 divided by Z1. Y2 is 1 divided by Z2. Y3 is 1 divided by Z3. Right? So this circuit refers impedance. This circuit refers the admittance. Current source in parallel with the impedance. Here current source in parallel with the admittance. Now we'll go for the further analysis. So now the current source are in parallel we can obtain single current source. Single current source equivalent to the combination. Let I be the current and Y be the admittance of the equivalent current source. So that I equal to I1 plus I2 plus I3. So the admittance Y equal to Y1 plus Y2 plus Y3. So by using that we can draw this diagram. Only one current source in parallel with the admittance. How to calculate this V? V equal to I by Y. That is I by Y1 plus Y2 plus Y3. I also I1 plus I2 plus I3. Right? So that V equal to I by Y, that is sum of currents divided by sum of impedance. Right? So this one can be converted into voltage source also. The same thing can be converted into voltage. Converting the above into equivalent voltage source. Voltage source means impedance is connected in series with the voltage source. Current source means connected in parallel. Voltage source means current connected in series. So we have V and Z. How will you calculate this Z? V is already calculated. V equal to I by Y. So this is the formula. Right? I1, I2, I3 divided. This I1 is nothing but V1, Y1, V2, Y2. So V can be calculated. How to calculate Z is 1 by Y. That is 1 divided by Y1 plus Y2 plus Y3. Right? So current source with admittance available. By using that we can convert voltage source into impedance. The voltage is calculated in terms of the sum of voltage and admittance divided by sum of admittance. This impedance is calculated 1 divided by sum of admittance. This admittance value available here. Now we'll go to the current source. This is depends upon the voltage source. Now we'll go to current source. Now consider this current sources. There are 3 current sources connected in series with 3 impedance. Consider 3 current sources of I1, I2 and I3 having internal impedance of Z1, Z2, Z3 connected in series. Our aim is to replace by a single current source, single source. These 3 current sources with internal impedance can be replaced by a single source. That is our aim. So the step 1 is convert each current source into equivalent voltage source. Into equivalent voltage source. So V1 is connected in series with the Z1. Current source means it is connected in parallel. Voltage source means it is connected in series. V1 Z1, V2 Z2, V3 Z3. This terminal A and B. Right? Now the current source, 3 current source with internal impedance are converted into voltage source with internal impedance. These are all connected in series. Current source means it is connected in parallel. Since all 3 voltage sources are series, replace them by a single voltage source and single impedance Z. How to calculate? V equal to V1 plus V2 plus V3. All are connected in series. Similarly, impedance also connected in series. Z equal to Z1 plus Z2 plus Z3. So that we can replace with a single voltage source and single impedance V and Z. Right. Now we'll see the equivalent current source. Again, how to convert into equivalent current source. So this is the current source is available, I and Z. Right? How to calculate I, V by Z? V is nothing but V1 plus V2 plus V3. Z is nothing but Z1 plus Z2 plus Z3. That just now we calculated. So I equal to this again. V1 is nothing but I1 into Z1. I2 Z2. I3 Z3. So that Z1 Z2 Z3. Right. So from that, how will you calculate Y? The admittance is 1 by Z. Is 1 divided by Z1 plus Z2 plus Z3. So now this current source with impedance is replaced by current source with admittance I and Y equal to 1 by Z. Right. So this I is calculated by using the formula. This Y is calculated by using this formula. So in this video we discuss about the Millman's theorem. Converting n number of current source or voltage source into single current source or voltage source. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Millman's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Calculate the current I in 4 ohm resistor in the network shown below using the Millman's theorem. So the network is given. there are two voltage sources available, 12 voltage and 20 voltage. The two resistors available, 3 ohm and 5 ohm, and one more resistor, 4 ohm. The question is, you have to find the current flowing through this 4 ohm resistor. It is termed as the terminal AB. So the Millman's theorem is nothing but the n number of current sources or n number of voltage sources are converted into single voltage source and single impedance. That is the main objective of the Millman theorem. N number of voltage source or n number of current source with internal resistance or impedance is converted into single current source or single voltage source with a single impedance. So here we have two voltage sources available. So the step one is we will convert these two voltage sources into single equivalent single voltage source. That is the first step. Similarly, there are two resistors available. Then we need to find the single resistance, equivalent single resistance. So the step one will go to the step one. In the given circuit, the two voltage sources are in parallel between the terminal A and B. One voltage source is connected one end of the terminal AB, another voltage source connected another end of terminal AB, so that it is parallel. So this circuit can be drawn as below. So this is the circuit is redrawn. So this is one voltage source with internal impedance 3 ohm. This is another voltage source with internal impedance 5 ohm. This is the terminal AB. In that we have the resistor R. Now we need to find the current I. Right? So the voltage source available this side is now transferred to that side. Now both the voltage sources are drawn in a same side. So we can convert this voltage source with a series impedance, series resistance. Another voltage source with series impedance can be converted into single voltage source and single resistance. So after converting this circuit become very simplified. We are having only one voltage source, one resistor and one load resistor. These are all connected in series. So we can easily calculate the current. I equal to V divided by R, sum of these two current. So that we are converting the two voltage sources into single voltage source with a resistance. Then how will you calculate this voltage and resistance? That is the second step. We need to find this voltage V and resistor R. See these two voltages are parallel. These two resistors also parallel. So there's a formula is available to calculate the equivalent voltage and equivalent resistance. Now we'll see how to calculate. We'll see how to calculate the equivalent voltage and resistance. So this parallel combination can be replaced by a single source of voltage V and internal resistance R. Then how will you calculate V? V equal to V1 Y1 plus V2 Y2 divided by Y1 plus Y2. So this is a formula available in the Millman's theorem. This Y is nothing but admittance. That is nothing but 1 divided by R1. Both are reciprocal. Resistance means opposing, admittance means allowing. So Y1 is nothing but 1 divided by R1. So that V1 into 1 divided by R1 plus V2 into 1 divided by R2 divided by 1 divided by R1 plus 1 divided by R2. Now all the values are available. V1, V2, R1, R2. The first voltage source is second voltage source. So that V1 is 12, V2 is 20, R1 is 3 ohm, R2 is 5 ohm. That is available in the diagram. Similarly, R1 is 3, R2 is 5. Right? So we need to simplify this. 12 divided by 3, 4. 20 divided by 5 also 4. Divided by, while taking LCM, we got 8 divided by 15. Right? So 4 plus 4, 8. 8 divided by 8 divided by 15. So 8 cancel. 1 divided by 15 will come to the numerator. So 15 voltage. So after simplifying, we got a single voltage source of 15 voltage. Right? Now we'll calculate the resistance. R equal to Y, that is 1 divided by Y1 plus Y2. I already told these both are reciprocal, resistance and impedance. So that we need to find 1 divided by Y1 plus 1 divided by Y1 plus Y2. Y1 is nothing but 1 divided by R1 plus 1 divided by R2. Right? R1 value is 3, R2 value is 5. Right? So while taking LCM, it is 8 by 15. While going numerator, it become 15 by 8. That is 1.875 ohm. Right? Now we calculated the single voltage source as 15 voltage, single resistance 1.875 ohm. So from this we can easily calculate the current flowing through the 4 ohm resistor. That is by Ohm's law, I equal to V by R. I equal to V by R. V is 15 voltage, what we calculated, divided by R plus 4. Right? R value what we calculated 1.875. This 4 is the load resistance. Right? This is the question. The current flowing through 4 ohm resistor. So after simplified diagram, we have only one voltage source and only one resistance and one load resistance. These two are connected in series, though it is added together. Both are added together. So 15 divided by 1.875 plus 4. That is 15 divided by 5.875. That is equal to 2.553 amperes. So current flowing through the 4 ohm resistor is 2.553 amperes. So in this problem, we calculated the current flowing through the 4 ohm resistor. It is marked as the terminal AB. In the given circuit, the two voltage sources with the two internal resistance available. So the Millman's theorem means the n number of voltage source or current source is converted into single voltage source or single current source. By using that, these two voltage sources converted into single voltage source with a single impedance. After that, the circuit is simplified. From the simplified circuit, we easily calculated the current flowing through the 4 ohm resistor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Millman's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, solved problem in Millman's theorem. Use Millman's theorem to determine the voltage across 50 ohm resistor in the network shown below. So this is the network is given. We need to find the current flowing through this 50 voltage across this 50 ohm resistor. Right? So here one voltage source is available, 60 voltage. Here another voltage source is available, 100 voltage. And 3 resistors, 20 ohm, 10 ohm and 30 ohm. So the Millman theorem means nothing but n number of current source or voltage source with the internal resistance are converted into single voltage source or single current source with the single impedance. That is the main objective of the Millman's theorem. So here also we can convert this. So two voltage sources can be converted into single voltage source. But in this problem we are going to use the formula. A formula is available. After converting, the resultant formula is available. By using the formula, we can find the voltage drop across the 50 ohm resistor. Right? So the step 1, first we'll follow the step 1. Step 1 is nothing but the given network is redrawn below. Let the terminal 50 ohm be 0 dash as shown in the diagram. So this terminal 50 we marked as 0 dash. Right? This only we need to find the, here only we need to find the voltage drop. Voltage drop across 50 ohm resistor is marked as 0 dash. And this terminal is marked as 1, 2 and 3. So the terminal 1 is connected with 60 ohm resistor, 60 voltage source and 20 ohm. Terminal 2 is connected with 10 ohm and 100 voltage source. Terminal 3 is connected with, there is no voltage source but 50 ohm is available. No need to consider this 30 ohm, right? So we consider these 3 terminal, 1, 2, 3. In terminal 1, the voltage source is 60, internal resistance is 20. In terminal 2, voltage source is 100, internal resistance 10. In terminal 3, voltage source is 0, internal resistance 50. So by using that, we can, if we consider this, we can use the formula directly. We can use the Millman's formula directly, right? 60 ohm, 60 voltage, 20 ohm. And 10 ohm, 100 voltage. 0 voltage, 50 ohm, right? So this is nothing but V01, V02, V03 is 0. So this is R1, R2, R3, right? So by using that, we can go for the second step. So the step 2, 20 ohm, 10 ohm, 50 ohm are connected to the common point O dash. let the other terminals of the resistor is marked as 1, 2, 3. Right? 1, 2, 3. All these resistors are connected to the terminal O dash. Right? So we'll refer the diagram again so that it is easier. So this 20 ohm connected in point 1, another end is connected to O dash. 10 ohm connected to point 2, another end is connected to O dash. This 50 ohm connected to point 3 and another end is connected to O dash. Right? So based on that we can write the formula as V01 is 60 voltage, V02 is 100 voltage, minus 100. It is connected in reverse order. See this, here plus minus, here minus plus. So that we have to take it as minus 100. Then V3, the voltage source is not available, 0. Y1 is 1 divided by R1, 20 ohm, 1 divided by 20. Y2 is 1 divided by R2, 1 divided by 10. Y3 is 1 divided by R3, 1 divided by 50. Here only we are going to find the voltage, right? So this is R1, R2, R3, 1 divided by R1, 1 divided by R2, 1 divided by R3. Now the 3 voltage sources with 3 impedance available, that can be converted into single voltage source. We are not converting into single voltage source, directly we are going to find the voltage. So VOO dash equal to V01 Y1 plus V02 Y2 plus V03 Y3 divided by Y1 plus Y2 plus Y3. So this is a formula available in the Millman's theorem, right? This Y1 is nothing but the admittance, that is 1 divided by resistance. Y1 equal to 1 divided by R1. So V01 is 60, Y1 is 1 by R1, 1 by 20, minus 100, V02 is minus 100. R2 is 10, so Y2 is 1 by R2, 1 by 10, plus V03, voltage source not available, 0. Y3 is 1 by R3, R3 is 50 voltage, divided by 1 divided by 20 plus 1 divided by 10 plus 1 divided by 50, R1, R2, R3. So this term is totally 0, right? 60 divided by 20, 3. 100 divided by 10 is 10, right? Here we are taking 100 as a LCM, so that 5 plus 10 plus 2. Here 5 times going, here 10 times going, here 2 times going. So 3 minus 10 is minus 7. This is 17 by 100. So minus 7 into 100 by 17. After simplification we got minus 41.2 voltage. So the voltage drop across 50 ohm resistor is, if we marked as 0, 0 dash, it is minus 41.2 voltage. So in this problem we use the Millman's theorem. From that we calculated voltage across the drop across the 50 ohm resistor, that is marked as 0, 0 dash. Millman's theorem means convert the n number of voltage source into single voltage source with the impedance. Here already the voltage sources are available. We marked as 3 terminals, 1, 2, 3, with 3 voltage source and impedance already connected. The third voltage source is 0. Other 2 voltage sources are available. But by marking all these 3, we can use this formula directly. So this is the formula, resultant formula by the Millman's theorem. By using the formula, we calculated the voltage drop across 50 ohm resistor. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the details about Tellegen's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The explanation of Tellegen's theorem, one of the theorem available in the circuit theory. First we will see the statement. In any network, the summation of instantaneous power or the summation of complex power of sinusoidal sources is 0. So if you consider any network, sum of the instantaneous power or complex power is equal to 0. The network may be linear, non-linear, passive or active, and time invariant or varying, whatever may be. Either there is linear or non-linear, passive, active, time invariant or varying, the instantaneous power is 0. For instantaneous power, the theorem may be expressed mathematically as summation of B equal to 1 to B, VB, IB equal to 0. This B into I is nothing but power. Power equal to voltage into current. B is nothing but starting from 1 to B for n number of powers, or if you add all the power in the network, that is equal to 0. That is the statement. In case of the complex power, the expression will be different. In case of complex power, where B is the number of branches in the network. For example, for complex power, the theorem may be expressed as B equal to 1 to B, SB equal to 0. What is that? SB is nothing but VB into IB star. That IB star is the complex conjugate of IB. Complex number means automatically we have real term and imaginary term. So that the star refers the complex conjugate of the IB. So in any network, the sum of the instantaneous power or complex power is equal to 0. This B equal to 1 to B means n number of networks, n number of branches. Right. The some more details available. We'll see the some more details available in the Tellegen's theorem. The above statement implies that energy must be supplied at the rate which is just equal to the rate at which energy is dissipated in resistor and stored in capacitor and inductor. So that is the meaning energy. What is the energy supplied is equal to energy dissipated. Energy dissipated means is dissipated in resistor. In case of capacitor inductor, energy is stored. So what is the energy rate supplied? That is dissipated in case of resistor, capacitor and inductor. So energy supplied is equal to energy dissipated. So that we are getting net power is 0. Thus the power delivered by independent source of the network must be equal to the sum of power observed in all other branches of the network, either dissipated or stored. So we need to understand that power delivered by the independent source of the network is equal to sum of power observed in all other branches of the network. Right? What is the power observed? That should be equal to power delivered, so that we can get the net power is equal to 0. Right? One important note is available. The branch voltages are arbitrary chosen with the only constraint that they satisfied KVL, Kirchhoff's voltage law. Right? So the net power in all the branches is 0. We are taking that this branches should satisfy the KVL. The branch current are also arbitrarily chosen with only the requirement that they are satisfy KCL, Kirchhoff's current law at each node. So this theorem states the instantaneous power or complex power is 0 in any network, whether it is time varying or invariant, linear or non-linear, passive, active, either it is normal power or complex power, the instantaneous power is 0, provided that it should satisfy the Kirchhoff's voltage law, branch voltages. Similarly, the node voltage, node or satisfy the Kirchhoff's current law, KCL, KVL and KCL. It should choose, you have to satisfy KVL or KCL, then only this statement is true. So in this video, we discuss about the details of Tellegen's theorem, statement of the theorem, mathematical expression and important points, that is power observed equal to power dissipated in they either by resistor, capacitor or inductor. Similarly, power what we delivered is should be equal to the power observed by all other elements, and also it should satisfy the KVL or KCL, Kirchhoff's voltage law or Kirchhoff's current law. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Tellegen's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will go to the topic. Verify the Tellegen's theorem for the network shown below. We need to verify the Tellegen's theorem for the network given in the problem. Now we will see the network. So this is the network given. One voltage source is available. Here one inductor, resistor, capacitor and another resistor. Here one capacitor is available. So the voltage across and current flowing, all the details are given. V1 to V6, similarly I1 to I6. And this network is given the naming is given P, Q, R, T, U. This is X, Y. This terminal is both are same, so that there is no name is available. So P, Q, R, T, U, and this one is X, Y. So the voltage V1, the source voltage is V1 and current is I1. This inductor voltage is V2, I2. For this branch QT, the current is I3, voltage is V3. For QR, we have capacitor, voltage is V4, current is I4. For PT, one more resistor is available, voltage is V5, current is I5. And this XY, one capacitor is available, voltage is V6 and current is I6. What is the Tellegen's theorem? Tellegen's theorem states that in any network, the sum of power, instantaneous power is equal to 0. Sum of the power means voltage into current, power equal to V into I. So the summation of V into I equal to 0 for any network, either normal power or complex power. So we need to verify that the sum of power available in this network, this V into I, is equal to 0. For that we are going to analyze the voltage. We are going to analyze the voltage for each and every loop. That should be equal to what is the voltage given. Similarly, the loop current, we are going to verify the loop current, right? So instead of power, we are going to verify voltage of each and every loop and current of each and every loop. That should be equal to 0 or as it is given in the value, right? So V1 is 4 voltage, V2 2 voltage, V3 2 voltage, V4 3 voltage, V5 minus 1 voltage, V6 minus 5 voltage. I1 is 2 ampere, I2 also 2 ampere, I3 4 ampere, I4 minus 2 ampere, I5 minus 6 ampere, I6 4 ampere. Now we will verify. First we will verify the voltage, right? First we will take this loop PQ, TUP, right? In this loop, this V1 equal to V2 plus V3. The voltage what we are applied is voltage drop across the element. So we will check later. First we will analyze the circuit. V1 equal to V2 plus V3. Then if you take this loop Q, R, T, Q, then what is that? V3. This V3 is equal to V4 plus V5. The voltage drop across equal to sum of the voltage drop across this branch. Both are same. Q, T is same as Q, R, T. Both are connected in parallel. So that V3 equal to V4 plus V5. Then take the another loop Q, R, T, Q. Right. And another one more loop P, Q, R, Y, X. This loop. If you take this loop, there is no voltage source. The sum of the voltage is equal to 0. V2 plus V4 plus V6 equal to 0. Right. So the first loop V1 equal to V2 plus V3. Second loop V3 equal to V4 plus V5. Third loop V2 plus V4 plus V6 equal to 0. Right. So that we will verify later. Now we will analyze. Similarly, we will analyze the current. What is this current I2? I2 is nothing but I3 plus I4. I2 is splitted into I3 and I4. What about this I4 is splitted into I5 and I6. What is this I6? I6 is nothing but I1 plus I2, right? So we will verify I2, I4, I6. I2 is nothing but I3 plus I4. I2 equal to I3 plus I4. I4 is nothing but I5 and I6. I5 plus I6. I6 is nothing but I1 plus I2, right? So these three voltages, the voltages in 3 loop and current in 3 loops are now analyzed. We will see the expression for this, right? First let us see whether the KVL and KCLs are satisfied. That is, Tellegen's theorem is telling some instantaneous power is 0 such that it should satisfy the KVL, Kirchhoff's voltage law and current law. First we will see the Kirchhoff's voltage law. First for the loop PQ, TUP, we already discussed. V1 equal to V2 plus V3. V2 is given 4, V2 given 2 voltage, V3 also given 2 voltage. So that 2 plus 2, 4 voltage. V1 equal to 4 voltage. Already V1 is given 4 voltage only, right? So by analyzing the KVL, we will got V1 equal to 4 voltage. Already the given value for V1 also 4 voltage. So it's satisfied. Now similarly for the loop Q or T cube. We already discussed V3 equal to V4 plus V5. V4 is 3 voltage. V5 is minus 1 voltage because it is going down. Right? So 3 minus 1, 2 voltage. V3 is 2 voltage. So this is also given. The value of V3 is 2 voltage. The given value of V3 also 2 voltage. By analyzing the KVL, we got 2 voltage. So it is satisfied. Right? So the one more loop is available for the loop of P, Q or X, Y, P. So here the source is not available. So V2 plus V4 plus V6 equal to 0. So V2 is 2 voltage, V4 is 3 voltage, V6 is minus 5 voltage, right? It is given in the problem itself. So 2 plus 3, 5, 5 minus 5, 0, right? So the equation is satisfied. Hence KVL is satisfied for all 3 loops, right? So we verified the Kirchhoff's voltage law for all the 3 loops. First loop having the source is available. So that V1 equal to V2 plus V3. In second loop, V3, the both are connected in parallel. So V3 equal to V4 plus V5. In third loop, there is no source. The total by adding all the voltage is equal to 0. So now we satisfied all 3 loops will satisfy the Kirchhoff's voltage law. Now we'll go to the Kirchhoff's current law. So by applying KCL, Kirchhoff's current law for the node P, Q and R respectively, we'll get the following equation. We already discussed I6 equal to I1 plus I2. That is I1 is 2 ampere, I2 also 2 ampere. That is equal to 4. So I6 is 4 ampere. So that we'll check with the given value. Similarly, I2 equal to I3 plus I4. We already discussed in the network. By diagram we already explained. So I3 is 4 ampere, I4 is minus 2 ampere. So 2 ampere. I2 equal to 2 ampere. I4 equal to I5 plus I6. That is minus 6 ampere. I5 is minus 6 ampere. I6 is 4 ampere. So minus 6 plus 4 minus 2. Right. So I6 what we got is 4 ampere. I2 what we got 2 ampere. I4 what we got minus 2 ampere. So these values are the given values also same. What we are got in this equation, that is given values also equal. So KCL is satisfied for all 3 nodes. Right. By applying KCL, we got the value of I6, I2 and I4 that is very equal to what is the value given in the problem also. So that it satisfied the KCL. Now we'll verify the instantaneous power. That is the important point of the Tellegen's theorem. K equal to 1 to 6. There are 6 nodes, 6 networks available. 6 branches are available. V1 to V6. Similarly, I1 to I6. Vk, Ik equal to 0. This is the mathematical expression of the Tellegen's theorem, right? So that summation of k equal to 1, Vk, Ik equal to 0. So in this problem, k equal to number of branches, that is equal to 6. So that summation of k equal to 1 to 6, Vk, Ik. That is we have to apply from 1 to 6. V1 into I1 plus V2 into I2 plus V3 into I3 plus V4 into I4 plus V5 into I5 plus V6 into I6, right? So from 1 to 6 branches are available. Now we need to substitute all the values. V1 I1 4 into 2, V2 I2 2 into 2, V3 I3 2 into 4, V4 I4 3 into minus 2, I4 is minus 2, V5 I5 minus 1 minus 6, V6 I6 minus 5 into 4. So we got 8 plus 4 plus 8 plus minus 6 plus 6 minus 20, right? So by adding all this value, what we got is 0, right? See this 6 minus 6 got cancelled. 8 plus 4 12, 12 plus 8 20. This is minus 20 is there. So it got 0, right? So that is the important statement of the Tellegen's theorem. Instantaneous power in any network is equal to 0. And also it should satisfy KVL and KCL. This already we verified. If this network satisfies the KVL and KCL, and also it satisfied the instantaneous power is 0. Hence the Tellegen theorem is proved for the given problem is for the problem given. So in this problem we verified the Tellegen's theorem. That is we verify with KCL KVL, then instantaneous power. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Tellegen's theorem. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Verify the Tellegen's theorem for the circuit shown below. We need to verify the Tellegen's theorem for this circuit. The Tellegen's theorem is nothing but for any circuit the instantaneous power, the sum of instantaneous power is equal to 0. That is the statement of the Tellegen's theorem, and also the circuit should satisfy the KVL and KCL, Kirchhoff's voltage law and Kirchhoff's current law. So in this circuit we need to verify this power delivered by this source is equal to power absorbed by these elements, resistive elements. We need to verify, right? We have to identify what is the total power delivered by this source. What is the total power absorbed by this resistor? Well, both are equal. That is power delivered equal to power absorbed. So in order to find the power, we need to identify what is the voltage across each and every resistor. There are 4 resistors available: R1, R2, R3, R4. The voltage across R1 is V1, R2 is V2, R3 is V3, R4 is V4. And the current is the total current. First current is I1. Then it is split into I2, I3, I4 with the resistor R2, R3 and R4. So we need to identify, we need to find the value of V1, V2, V3, V4. Similarly I1, I2, I3, I4. From that we need to find what is the voltage drop, power across the resistor, and what is the power delivered by the source, right? So in this circuit, by analyzing, it is clear that these 3 resistors are connected in parallel. R2, R3, R4 are connected in parallel, and also it is given R1 value is 1 ohm. This R1 is 1 ohm. R2, R3, R4 is 2 ohm. All the resistors having same value, 2 ohm, and this also 2 ohm. Then what is that? The voltage drop across R2, R3, R4 are equal because it is connected in parallel, and also values are equal. Similarly, the current flowing through the resistor R2, R3, R4 also equal because of same value of resistor. That is I2, I3, I4 also equal. I2 equal to I3, that is equal to I4. V2 equal to V3, that is equal to V4, right? Now we'll find the values. Now first we'll find the total resistance of this circuit. What is the total resistance of this circuit? These 3 are connected in parallel, that is in series with the R1, right? So first we'll find the total resistance. Then we'll find the total current. From that we can find the voltage V1, V2, V3. Then we'll find the I1, I2, I3. From that we can find total power, right? Now we'll go to find the total resistance of this circuit. Let the first calculate the various currents and voltage drop. For that, first what we need? Total resistance or parallel. That is, these 3 resistors are connected in parallel. 1 divided by 1 by 2 plus 1 by 2 plus 1 by 2. That is 1 divided by 3 by 2, that is 2 by 3, because all the values are equal. If it is all the values are equal, we can use this formula: 1 divided by the resistor value, 1 divided by 1 by R value, right? So that it is 2 by 3 ohm, right? So then what is the total resistance R total? R total is nothing but 1 plus Rp, right? The resistor R1 equal to 1 ohm, then the parallel resistor. So 1 plus 2 by 3, that is 5 by 3. The total resistance of the circuit is 5 by 3, right? So the first resistor R1 is 1 ohm, that is parallel with this, series with this parallel resistor. So that it is 5 by 3 ohm. This one is nothing but the resistor R1. This is R2, R3, R4. All values are equal. So from that we can find the source current, that is equal to I1. Both are equal. Now we'll refer the diagram again. This is R1. R1 value, that is value is 1 ohm. This R1 is series with this parallel combination. So that 1 plus 2 by 3. Similarly, the source current is equal to current I1. Both are same. The source current equal to Is equal to I1 because R1 is connected in series with the source. So that is Vs by RT. Vs is 100 ohm, 100 voltage. The total resistor is 5 by 3. So it is 100 into 3 by 5, that is equal to 60 amperes. So the voltage, the source current as well as the current I1 is 60 amperes. From that we can find V1. V1 equal to I1 R1. I1 is 60 amperes. R1 is 1 ohm, 60 voltage. Right? So the I1 is equal to 60 amperes. V1 equal to 60 voltage and also source current also 60 amperes. Now we will find the voltage drop across each and every element. Vs equal to V1 plus V2. In a closed loop, Vs equal to V1 plus V2. We will refer the diagram. So this is the closed loop. The voltage 100 what delivered is equal to voltage drop across R1 and R2. So 100 equal to V1 plus V2. Vs equal to V1 plus V2. The voltage what we applied is equal to voltage drop across R1 and R2. Based on that, Vs equal to V1 plus V2. From that, V2 equal to Vs minus V1. Right? Vs is 100 voltage. V1 what we calculated is 60 voltage. So 100 minus 60, 40 voltage. So V2 equal to 40 voltage. We know that this V3, V4, V2 all are equal. We already discussed all the resistors are connected in parallel and also the resistor values are equal. So the voltage drop across R2 is V2, that is equal to V3, V4. Voltage drop across R3 as well as R4. All are 40 voltage. Since the voltage is same across the parallel combination. Right? So now we calculated V1, V2 as well as V3, V4. Right? V1 is 60 voltage. V2, V3, V4 is 40 voltage. Then I2, I3, I4 that also equal. That is the total current. The total current is 40 amp. 40 divided by 2 is 2 ampere. Right? The 40 voltage is available across the V2 divided by the resistor is 2. I equal to V by R. V is 40 voltage, R is 2. So 20 ampere. The 20 ampere is flowing through the current, each and every resistor. I2, I3, I4. And also the total current is 60 amperes. So there are 3 resistors available. So equally divided 20, 20, 20. Right? Current across R2 is 20 ampere, R3 is 20 ampere and R4 is 20 ampere. The 60 ampere is 3 divided by 3. Equally divided by 3. So 20 ampere. That also another calculation. Otherwise I equal to V by R. V is V2. The I2 is V2 by R2. 40 by 2, 20 ampere. So now we can find the power delivered by the source. Vs, Is. Vs is 100 voltage. Is what we calculated 60 ampere. That 60 ampere only divided into 20 voltage in 3 resistors. So it is 6000 watts. Power delivered by the source is 6000 watts. Now we need to verify the voltage drop across each and every resistor. Power drop across each and every resistor should be 6000. That is the Tellegen's theorem. Power delivered equal to power absorbed. So that net power is 0 in any network. Sum of power in any network is 0. Now we calculated V1, V2, V3, V4, I1, I2, I3, I4. Then we calculated the power delivered by the source. Now we'll see power absorbed by the resistors. So total power dissipated by the resistor equal to, there are 4 resistors available. So V1, I1, V2, I2, V3, I3, V4, I4. Right? This is the first resistor connected. Then these 3 resistors are connected in parallel. R2, R3, R4. So we know the value of V1, V2, V3, V4 as well as I1, I2, I3, I4. V1 is 60 voltage. I1 is 60 ampere. Right. V2 is 40 voltage. And V3, V4 also 40 voltage. Similarly, I2 is 20 ampere. I3, I4 also 20 ampere. Right. The voltage across R2, R3, R4. Similarly, current flowing through R2, R3, R4 also equal. 40 into 20. So 60 into 60, by simplifying all this, what we got? 6000 watts. Right. So this power dissipated also is 6000 watt. Earlier we calculated power delivered. power delivered by the source also 6000 watts. So as power delivered is equal to power dissipated in the circuit, the Tellegen theorem is said to have been verified. Right? So power delivered as well as power observed is what we calculated are equal. So that the Tellegen theorem is verified. So in this problem, we verify the Tellegen's theorem. First we calculated the voltage across each and every element, current through each and every element, then power delivered by the source, then power absorbed by the each and every element. If both are equal, we observe that both are equal. So the Tellegen theorem is verified. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.